So part 3 is all about vision. This image here is a self-portrait of M.C. Escher. That's the artist that we talked about in part 1. So some visual neuroanatomy here. These are the types of structures that you're going to want to know. The lens here, the cornea, the fovea. The fovea is the part of your retina that is receiving information from what you are looking at directly. So it is directly at the back of your eye. And then the retina, the black, thick area, the back of your eye, and your optic nerve. Those are really the structures that are going to be most important when we talk about the visual system. So some physics of vision. What we are detecting with visual stimuli is actually waves, specifically light waves, and those light waves have a wavelength and they have a wave amplitude or height, just like ocean waves have a height, and they have a purity. In other words, are they a beautiful, curvy, luscious sine wave, or are they a little more erratic? So do they have little etchy, sketchy, zigzaggy parts to their wave? So those are the three features of the light wave that we're interested in. As you can see there, the total range of waves, at least here on the Earth, would start with radio waves at the longest. They are 1,000 meters long, all the way down to gamma rays, which are measured in nanometers, in fact 1 in 10,000th of a nanometer. The visual section of light is somewhere in the middle, still measured in nanometers, but running from about 380 to 750 nanometers. Longer wavelengths are perceived as red. The shorter wavelengths are perceived as purples and blues. In the middle, you've got your greens and yellows. Okay, so wavelength is detected as color for us. Amplitude, or how intense that light wave is detected as brightness. And then the purity, or whether or not it's a beautiful, perfect sine wave or has some zigzag to it, that is detected as saturation or richness of color. So here's some visual neuroanatomy. And frankly, if you're not a little bit confused by the end of this slide, then you probably were not paying attention well enough. So let's look at the left-hand part of the slide. The light is coming in from the front of the eye, which is really the left, to the left of the slide. The light first has to pass through a layer which contains a whole bunch of nerve fibers. It also contains some blood vessels and whatnot. Then it has to pass through the ganglion cells, which is the third sequence, or the third in the sequence. Then it has to pass through the bipolar cells, which is those are the second in the sequence. Then it has to pass all the way through the rods and cones. Okay, so if I were designing this system, I would probably have turned everything around. I would have had the rods and cones facing the front of the eye. So they're basically ready to receive that light. But no, I'm not the one who designed the system, so the light actually has to pass through all these layers of cells before it gets to the part of the rods and cones that are sensitive to light. So let's look over on the right-hand side. The very end tips of the rods and cones, those are the parts of the cell that are responsive to light. They are partially embedded, though, into a dark pigment at the very back of the retina. Again, I don't know why it was designed this way. But when light comes in through the front of the eye, it travels through all of these layers of cells until it gets to the part of the rod or cone that is sensitive to light. That will trigger an electrical signal in the rod or cone. That signal is collected by the bipolar cells, which transmit it to the ganglion cell. Bipolar cells you can think of as kind of like the interneurons in the spinal cord, because they really don't go anywhere. They're just short little nubby things that are responsible for processing or summating basically the visual signal. The ganglion cell, though, that's kind of like the spinothalamic cell because it originates in the retina, and then the axon of the ganglion cell actually travels out of the eye all the way into the brainstem and then up to the thalamus where it terminates, right? So the ganglion cell is kind of like the spinothalamic cell, but because it originates in the retina, we would really call it the retinothalamic cell, wouldn't we? Anyway, the axons of the ganglion cell are bundled together to form the optic nerve. Okay. Let's look at those rods and cones. They are specially designed to be able to detect light, and when they detect light, they they trigger an electrical signal, which is really a graded signal. It's not an action potential, but they send that graded signal to the bipolar cells. Rods here are shown in black and white, and the cone is shown in color. Why? Because this is a mnemonic. This is a way to help you remember that rods are only sensitive to light. They're not, they cannot tell you anything about color. Cones, on the other hand, can detect color. In fact, certain cones are specifically designed to detect certain wavelengths of light. So this is showing you right at the back of the eye, directly behind, if you drew a straight line through the lens and through the viscera of the eyeball, all the way to the back, that's the fovea. And the fovea is where we are detecting what we are looking directly at. The fovea is made up largely of cones, very few rods. So that's what it's showing there. Showing you there at the edge of the fovea, you've got almost all cones, and then as soon as you get towards the outer edges of the fovea, then you have more rods. Why is that the case? Because cones are sensitive to color, and we want to be able to look at something and tell what color it is. And rods, on the other hand, are really, they're only sensitive to the presence of light, but they're much more sensitive than cones are to lower levels of light. And that is a beautiful tree, a photograph I took on a hike last year, I think. Let's talk about visual receptive fields. And just as a reminder, the receptive fields in the somatosensory system are the patches of skin to which a particular somatosensory cell is sensitive, right? So you talk about a receptive field for a particular somatosensory cell. So you'd say the receptive field for that somatosensory cell is this little patch of skin. For visual receptive fields, we usually talk about it in terms of the ganglion cell. So we would say the receptive field for this particular ganglion cell is this particular area on the retina, because it is sensitive to light that shines on that part of the retina. Now there are about 1 million axons. In other words, there are about 1 million ganglion cells that form the optic nerve. But there are 130 million rods and cones. What that means is there are hundreds of rods and cones that are funneling into each ganglion cell. So one ganglion cell is potentially sensitive to the area where there are hundreds of rods and cones feeding into it. But not all rods and cones, not all ganglion cells are created equal. The ganglion cells in the fovea, they have very few cones that funnel into one particular ganglion cell. Those receptive fields are very small. The ganglion cells that are in the periphery of the retina, they have hundreds and hundreds of rods that all funnel into one ganglion cell. So their receptive fields are much larger. Each ganglion cell has a receptive field, though. It has a spot on the retina to which it is sensitive. And it is sensitive in the sense that it not only tells you whether it detects light, but it tells you whether there is zero light. Like many other neurons, rods and cones have a base rate of firing, just a normal beat, just a bump, bump, bump. They're sending off a signal. This greatly increases the sensitivity or the communication potential for that cell, because it not only tells you that it has received a stimulus by increasing the rate of firing, but it can tell you that there has been some sort of depression, some inhibition by reducing the rate of firing below that base rate. The ganglion cell will respond when it has received the appropriate type of stimulus to its receptive field. So the word appropriate is important there. Here you see a ganglion cell. It happens to be fed into by only one bipolar cell, and that one bipolar cell receives input basically from just a couple of cones. That's what this is showing you here. This ganglion cell, no doubt, originates in the fovea. We need very small receptive fields in order to have fine discrimination, in order to see very fine details in your fovea. But this also shows you a peculiar aspect of the receptive fields of ganglion cells. The center of the receptive field is usually responsive to the opposite, or it will have the opposite response to stimulation than the surround. Okay, so if you shine a light, for example, on the center of this receptive field, this whole receptive field, if this one is an on, center, off, surround, then you will cause the ganglion cell ultimately to turn on, to start firing much faster than its base rate. On the other hand, because center and surround are always opposite, if you shine a light into the surround of this receptive field, you will actually inhibit the ganglion cell, because again, we're assuming that this is an on-center, off-surround receptive field. So all the receptive fields of ganglion cells are like that. They have a center and a surround, and they are designed to be opposites in terms of what they will do to the firing rate of that ganglion cell. So again, the stimulation that is appropriate for that ganglion cell is unique to the cell, and it is dependent upon which receptor is being stimulated, and then the intermediate cells. I'm sorry that you can't see the text behind it, but it's basically saying the stimulation is dependent upon the receptor and the intermediate cells, meaning that the response of the ganglion cell depends on whether it is receiving input from rods or cones, whether it's receiving excitatory and inhibitory input, whether it's a color stimulus. Whether or not you get a response in a ganglion cell also depends on the location of the receptors. So let's look at the anatomy of that retina one more time. So remember, you have light coming in from the left-hand side of your screen here, and it has to pass through blood vessels and fibers, and then it passes through the ganglion cells and the bipolar cells, and then gets to the rods and cones at the very back, and the light is detected by the rods and cones. That creates an electrical signal. It's a graded signal that's sent to the bipolar cells, and the bipolar cells funnel into ganglion cells. So the ganglion cells then are basically your retinothalamic cells. So those axons travel out of the eye, past the optic chiasm, into the midbrain, up into the occipital, or excuse me, into the thalamus, where they synapse, and then the next set of cells start at the thalamus and go back to the occipital lobe. Okay, so each ganglion cell, then, the receptive field of that ganglion cell is composed of the area where each of the rods and cones are that are sensitive to light and that feed into that particular ganglion cell. So what happens after you have light that has traveled into the retina and it has been detected, sent through the bipolar and into the ganglion cell? So ganglion cell axons, again, form the optic nerve. So they exit the eye and they travel back to the optic chiasm, chi meaning X. It just looks like the letter X. But before we talk about what happens, the magic that happens at the optic chiasm, look at the the visual field in the front. You see in the right hand side it looks bluish, left hand side looks more lavender. We have this tendency sometimes to assume that information or visual stimuli on our right body side must go into our right eye, and the information from the left body side must go in the left eye. So blue information would go in the right eye, purple into the left. Not so. Everything in front of you goes into both eyes. But because of the way the lens works and the way the light travels in a straight line, because all of that, that information is sent out of the eye by virtue of the axon of the ganglion cell. It travels to the optic chiasm, and there all the information from the right visual field is sent to the left thalamus, and all the information from the left visual field is sent to the right thalamus. Now it's the thalamus where the ganglion cell axons synapse, and then the information is carried by another set of cells to the occipital lobe and to other places, but we won't talk about those at this point. Here's another look. Everything on the right visual field, so the trees, goes into both eyes, but everything is separated out at the optic chiasm so that the trees on the left are only seen, the trees on the right are only seen by the left occipital lobe, and the house on the left is only seen by the right occipital lobe. Also, not only is the image switched so that everything on the right goes to the left, but it's upside down. It's projected upside down. Okay, so let's talk about how this comes together. You have all these ganglion cells with round receptive fields. Now they are round, but they have a center portion and a surround portion, and those are opposing each other, but they're round. Each of those ganglion cells is connected to a specific cell in the thalamus. Those thalamic cells are projected to what we call simple cells in the occipital lobe. In fact, ganglion cells that have adjacent receptive fields. So receptive fields right next to each other in a line. Those all feed into the same simple cell. So we have ganglion cells with adjacent receptive fields feeding into one simple cell in the occipital lobe. The simple cell receptive field then is actually shaped like a bar of light instead of a point of light. It's really those circles all lined up next to each other. When you do that, it's going to be sensitive to a bar of light. But it's only going to be sensitive to a bar of light in a specific orientation. Up and down, horizontal, some kind of angle. And only sensitive to a particular location on the retina. So simple cells, just like ganglion cells, are tied to one part of the retina. Simple cells feed into complex cells there in the occipital lobe. Those complex cells then have receptive fields that are usually a bar of light, but that bar of light can be anywhere on the retina. Okay, so there's a receptive field of a complex cell. It will, if there's no light, it's going to have a baseline level of cell activity. That's just its normal beat. It's just saying I'm hanging out, nothing going on, bump, 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 just sending out a signal every so often. But then you put a bar of light in there at a 45-degree angle, and you go bump, 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 bump. So it's all excited. There's something in its receptive field, and it doesn't seem to matter where on the retina you put that bar of light, you still get that strong response, as long as it's 45-degree angle. Now you knock it up to 60-degree angle, all of a sudden it's a little stronger than the base rate, but not by much. You get a bump, 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 bump. And then if you tilt it to where it's a 15-degree angle, then you get no response. Not just a baseline level, but it has dropped down below to inhibition. So people talk about feature detectors then. So we think about complex cells responding to specific features. Some complex cells respond to a bar of light in a particular length and a particular orientation. Some of them require movement in order to fire, but location on the retina really doesn't matter. So here's an example of 3 ganglion cells that all feed into the same simple cell. And because they feed into the same simple cell, and they have adjacent receptive fields, then you end up with a bar of light as your receptive field for this simple cell. This should be tempting to think of this as a possible mechanism for all basic visual perception. Maybe we can add these features together. A line of certain orientation, it's got to have movement and so on. Those are features that we can put together to figure out what it is we're looking at. But we need to make one pit stop first, and that is color vision. Your book is going to talk about how there's a trichromatic theory of color, and there's opponent process theory of color, and one is true and the other is true. That's accurate. Trichromatic theory of color is true at the level of the cones. So there are 3 cones that are sensitive to different aspects or different portions of the visible light. The opponent process theory is true, though, at the level of the ganglion. By the time you input multiple cones and then multiple bipolar cells into one ganglion cell, you end up with a ganglion cell that is responsive to color, but using the opponent process theory. How about we call it good? There's one thing I do want you to know, though, and that is that there are 3 types of cones, and they respond maximally to different wavelengths, which correspond to different colors. although the retinal ganglion cells respond differently to points of opposite colors. So points of red and blue, or points of blue and yellow. Now, I literally mean they respond oppositely. So upper left-hand corner, if you have a red on, green off, that means you put red in the center, you're going to get an on response for that ganglion cell. You put green in the outside, anywhere in the outside of the receptive field, and you're going to get an off response in the ganglion cell. You can have the opposite, red off, green on. You can have the opposite, meaning green in the center, red in the outside. You can have all combinations of blues and yellows, but they're all opposites. Okay, so that's pretty cool though, right? We've got these feature detectors. It looks like we can build a visual system. So for example, if the word clock were in front of you, then you would be able to detect the features. There's a curvy line in this orientation in this spot, and then there's a curvy line this way, and the curvy line, and there's a straight line right here at this particular part of the visual field, and then there's also one that's straight down below it, and so on. So you've got enough information here to really draw a conclusion that the first one is a C, and the next one's an L, and the next one's an O, and so on. All the way up the ladder until you are able to detect that the word is clock. So that seems reasonable because we have cells that respond to bars of light in a particular orientation, and we have edge detectors. We've discovered that. There are certain cells that are good at detecting edges. We have movement detectors. We've got color. We have special cells that detect the presence of faces. Nothing else. So it seems like we should be able to recognize objects just by having these cells funnel into increasingly complex objects or shape detectors. So then we would have, for example, a cell which represents our grandmother, and another cell which represents yellow Volkswagens. So how's that sound? Sound reasonable to put that together and call it good? So it feels like we should be able to use this process to really build a visual system, right? I mean, after all, Google does it with faces. I mean, it will recognize faces even if they're turned to their side or partially obscured. It can even tell you what the emotion is for some of those faces. But not really. It's actually, our visual system is much more complicated than that, which is why, thank goodness, it is more accurate than Google. There are what we call bottom-up processing mechanisms and top-down processing mechanisms. Bottom-up mechanisms would be those that rely entirely on detecting the various features of the object in order to figure out what it is. So you see someone is breaking down the features of a giraffe. You've got edges, you've got groupings, you've got figure to ground, and you've got explicit spatial relationships between different lines. So if you put all that together, hopefully you'll be able to come up with the idea that, oh, I'm looking at a giraffe. On the other hand, we probably do some of that in combination with top-down. Top-down is basically generating a hypothesis about what you're seeing and then testing that hypothesis. I wonder if that could be a monkey. I wonder if that could be a lion. I know I'm at the zoo. I know it's moving around and making noise, so it's probably an animal. I wonder if it could be X type of animal. So from the top, you generate ideas and test them. And that is in combination with feature detection. So you're looking at the edges, you're looking at the various spatial relationships of those different lines formed by that animal, and you're using top-down hypothesis testing to figure out exactly what it is you're looking at. Here are the problems with assuming that all of our visual information is processed using a bottom-up or feature detection approach. We really do have a heck of a lot of cells, but not that many. The sheer complexity and volume of having cells that can detect or recognize very specific objects is mind-boggling. The number of objects that we would need to know and the number of cells we would need to have. And in fact, we would be here until next Tuesday really just trying to figure out what the title of the slide says. So speed isn't a problem. Also, Grandma, you know, she looks different from when we look at her from the side. But we still can perceive her as Grandma no matter what orientation she's looking. And that's known as object constancy. That's a problem for feature detection. And it doesn't really explain the principles of the Gestalt or visual illusions, which we won't cover here, but I'm pretty sure there are some aspects of that in your text. It also doesn't explain why we fail to notice misspelling or extra words. And the answer, as usual, is that it's probably a combination of theories, a combination of bottom-up processing and top-down processing. So if you can read this, that would be an example of a combination of using features like individual letters, but also top-down. So you are projecting what you think would be next. You're creating a guess or a hypothesis about what would come next. I'm looking for a noun. Looks like it probably starts with R and ends in CH. It has something to do with reading and the human mind, and it's probably related to Cambridge University. So that kind of thing, you're using lots of information to hypothesize as to what you are looking at. Oops. So here's an example. Can you find the mistake? And again, our top-down mechanism says, oh, the mistake must be down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, okay. Look at it. 1, 2, 3, 4, 5. No, that looks perfect. Well, the mistake, of course, is the double the. Can you find the mistake? Don't worry, I'm not going to test you on that. But this just shows you that top-down processing in combination with bottom-up processing is fairly complex. We're doing constantly a constant balance between take a guess, check your guess, take another guess, check your guess, and so on. I'm going to call it a complex but efficient dance between bottom-up and top-down. This is a picture of a truck with a large pile of manure in the back. The reason I have this picture here is to tell you the story of a classic case of top-down processing. So I decided, I got it into my head I was going to do some composting. And typical Dr. Kurth style, I got several books from the library, read all about it, and then I designed my own compost bin, and I knew exactly what the dimensions would be. I also knew exactly how many layers of what I would need. You need X inches of green, and then X inches of brown or carbon-based, and then X inches of green again, and so on in layers. So I had it all calculated out, how many cubic feet of fresh manure I would need, because that you need your carbon-based materials, and then you need your nitrogen-based materials. And your best source of nitrogen is fresh off the rack manure. So I wrote this down for my husband. I made arrangements with a local horse barn that he could come and get some of their very fresh manure. And then I wrote it down on a piece of paper, 1-inch block letters. I said to him, I want you to get 4 to 5 cubic feet of manure. And he looked at that, and he looked at me puzzled, and he said, that's a lot of manure. I told him, no, it isn't. And my mistake, of course, was not to patronize him. I decided not to say to him, well, if you think about it, the width of the truck is about 4 or 5 feet wide. So 4 or 5 cubic feet of manure would be 1 foot by 1 foot by the width of the truck. That's all you need. Well, he comes back sometime later with a truck absolutely filled to the brim with manure, just like this truck here. And he says to me, "Where do you want me to put it?" I thought, what did you just do? I asked you for 4 or 5 cubic feet and you bring me an entire truckload. I have no idea what to do with it. Turns out he was using top-down processing, even though that letter, those instructions were sitting right next to him on the seat of the truck, and it clearly said 4-5 cubic feet. He had translated that into cubic yards. Every time I said cubic feet, in his brain he heard cubic yards. Why? Because most things are sold in cubic yards. Compost is sold in cubic yards. Concrete, sand, really, you name it, and it is sold by the cubic yard. So that's what he heard. That's what he thought he saw. Cubic yards. There are some fascinating disorders of visual perception. Visual agnosia. This is where you can see the objects, but you really just cannot tell what they are. And visual agnosia is specific to the visual system, so you can tell what the object is in other systems. So if you hold up a set of keys to someone who has visual agnosia and you say, "What are those?" they could describe them. Well, they're a bunch of shiny things. They're kind of long and narrow, and they seem to be attached to each other with a round, shiny object. So they can describe it for you, but they can't tell you what they are. But then if you jingle the keys, jing, jing, then they'll say, oh yeah, okay, those are keys. They'll know immediately what it is. Prosopagnosia is a special form of visual agnosia. This is where they cannot discriminate faces. So they can point to where someone's nose is on their face. They can describe, okay, this person is black, or this person has Chinese or Asian eyes or something, but they really cannot tell one person from another. Anton syndrome. I had a patient with, I've had a couple patients with Anton syndrome actually. This is where they think they can see, but they can't. Right. They think they can see, but they cannot. So my most memorable case of this was during my postdoc. We had a gentleman who went in for surgery, and he had a complication, and part of his basal ganglia and occipital lobe were damaged. He thought he could see, but he was just making up information about what he was able to see. So he had Anton's syndrome. And that is an adorable little spider.